Have you ever noticed your fruit rot over time? This is an example of a chemical reaction. A chemical reaction is the ability of a substance to undergo a specific chemical change, changing the composition of its matter. The reactant being what you started with, fresh fruit, and your product is the substance produced, the rotten fruit. To calculate how much reactant is needed, you need to balance chemical equations. You need to know the quantity of one substance in a reaction to calculate the quantity of any other. Calculations using balanced equations are called stoichiometry. This is an example of an unbalanced equation. A balanced equation has the same number of each type of atom on both sides of the arrow. First, you need to write the amount of atoms on each side of the chart, the left being reactants and the right being products. What you multiply on one side has to be multiplied on the other. Mole ratio is the ratio of moles of one substance to the moles of another substance in a balanced equation. The small numbers are the numbers of atoms, while the coefficients are the number of moles. This is the formula to determine the moles of a desired substance. This is an example of a mole ratio problem. Our half is 4.5 moles of water since it's what's given, and our 1 is the moles of O2 since it's what we're trying to find. We divide 4.5 moles of H2O by 2 moles of H2O since it's what's given in our balanced equation. Our answer is 2.25 moles of O2 since the H2Os cancel out. A limiting reactant is the first reactant that's used up in a reaction. When it's all used up, no more products can form and the reaction stops. Here's an example. For every 2 cups of cake mix, you need 1/2 cup of water to make 1 layer of cake. How many layers of cake can you make with these quantities? You can make 2 layers of cake because we run out of water, making water our limiting reactant and the cake mix our excess reactant since we still have 2 cups left over. We commonly see these limiting reactants in cooking meals or preparing drinks. Intermolecular forces are forces between molecules. They determine whether a molecule is a solid, liquid, or a gas at any given temperature. From weakest to strongest, it's London dispersion, which has a temporal partial charge, dipole-dipole, which is between the positive end of one polar molecule and the negative end of another polar molecule, and hydrogen bonding, which can be between hydrogen and nitrogen, hydrogen and oxygen, and hydrogen and fluorine. In solids, atoms are packed closely together and they don't move around. Some examples include an apple, a rock, and a pencil. In liquids, atoms are close together but some can move around. Liquids take the shape of the container. Some examples include juice. A gas either takes the shape of its container or it spreads out because the atoms move freely. An example includes helium, which can be found in helium balloons. The formula for the ideal gas law is PV equals nRT. Pressure is how often the atoms hit the sides. Volume is how big the container is. Moles is how many particles there are. The R is your gas constant. You pick the right one according to your units for pressure. Temperature is how fast the particles move. Instead of having different formulas for Boyle's law, Charles' law, and Avogadro's law, we can just sum them all up into the combined gas law, and you can get rid of the values that you don't need according to what the problem is asking. IV fluids are full of specific solutions that can be used to treat patients. In order to create an isotonic solution, it is essential that all concentrations are carefully calculated so that the amount of solute is just right to create a solution. IVs are used daily in hospitals to treat patients. They are used to deliver fluids and medications. A solution is a stable, homogeneous mixture. A solution is made up of a solute and a solvent. Soluble means that it's able to dissolve in, while insoluble means that it's not able to dissolve in. Factors that can change how fast a solute dissolves include stirring, temperature, and surface area. Water itself is an example of a homogeneous mixture. Another example includes laundry detergent. The air that you breathe is a homogeneous mixture of oxygen, nitrogen, argon, and carbon dioxide, along with other elements in smaller amounts. These are the formulas for calculating molarity, molality, and percent concentration. Acids taste sour, turn blue litmus paper to red, and have more H+ ions than OH- ions. Bases taste bitter, turn red litmus paper to blue, and have less H+ ions than OH- ions. Some examples of acids include lemons, vinegar, and stomach acids. An example of a base is baking soda. These are the formulas to find pH, H+, POH, and OH-. Reaction rates are how fast or how slow the reaction takes place. Activation energy is the minimum energy needed to initiate or start a reaction. Collision theory states that atoms, ions, and molecules can react to form products when they collide with one another, providing they have enough kinetic energy and they're in the proper orientation. Factors affecting activation rates are temperature, concentration, particle size, the use of a catalyst, and surface area. A catalyst is a substance that speeds up the rate of reaction by lowering the activation energy. An endothermic reaction absorbs heat from its surroundings while its surroundings cool down. An exothermic reaction releases heat to its surroundings while its surroundings heat up. An example of an endothermic reaction is melting ice cubes, while an example of an exothermic reaction is making ice cubes. Chemical equilibrium is when the rates of the forward and reverse reactions are equal. Equilibrium also means that the reactions have reached a state of balance. A combined reaction uses a double arrow, which tells you that the change is reversible. Le Chatelier's principle states that if a stress is applied to a system in dynamic equilibrium, the system changes in a way that relieves stress, disrupting the equilibrium. Thermochemistry is the study of energy changes that occur during a chemical reaction. Heat is represented by Q or delta H, and is the energy that transfers from one object to another because of the temperature differences between them. The law of conservation of energy states that in a chemical or physical process, energy is neither created nor destroyed. This chart outlines the phase changes and the heat changes between them. They also show the proper formulas you need to use to determine how much energy is needed to reach that state. This chart shows the phase changes from a gas to a solid.